Today, we're going to dive deep into the core of Erlang/OTP. You know, the secret sauce that lets giants like WhatsApp handle billions of messages a day without breaking a sweat. We're going to break down how Erlang pulls off this massive concurrency, and it's not with complicated locks and all that mess. Nope, it's a super simple, really elegant idea, kind of like an old-school postal service. But first, let's just chew on this for a second. How would you build a system for millions of people that can never fail? I'm talking about things like telecom switches, financial trading platforms, or those huge messaging apps. This isn't some academic puzzle. It's the exact real-world problem Erlang was invented to solve like 30 plus years ago. You know, the usual way we handle concurrency, it's often this total mess of different threads, all trying to grab the same piece of memory. And what does that get you? A nightmare of locks, race conditions, deadlocks. It's just so fragile and a huge headache to get right. Erlang's approach is, it's completely different. It's called the share-nothing model. The idea is simple. Instead of sharing memory, every little component is totally isolated. And just by doing that, an entire category of bugs just vanishes. Gone, right from the start. So how does Erlang actually do this? Okay, here's what we're going to cover. First, we'll look at the fundamental building blocks, processes and messages. Then we'll get into how supervision helps create systems that can literally heal themselves. After that, we'll dive into the gen server, which is a standardized decision loop. And finally, we'll put it all together to see the true power of OTP. All right, so if we're not using threads and shared memory, what's the alternative? Well, the answer is the Erlang process. And this, right here, is the absolute cornerstone of everything in an Erlang system. Now, when I say process, I need you to forget everything you know about heavy operating system processes. That's not what we're talking about. An Erlang process is incredibly lightweight. Think of it like a tiny, self-contained little computer. They are so cheap to create, so fast, that you can spin up millions of them on a single machine, no problem. And every single one is completely isolated from all the others. And making one? It's ridiculously easy. It's just a single function call, spawn, and boom, you've got a new concurrent actor running in your system. And this simplicity, that's the whole point. It encourages you to use processes for everything. Got a web request? Spawn a process. A new user connects? Spawn a process. Any tiny background job? You guessed it, spawn a process. Okay, so you've got millions of these totally isolated processes running around. How on earth do they talk to each other? Well, they send messages. That's it. Seriously, that's the only way they can communicate. You use the send operator, which is just an exclamation mark, and it fires off an asynchronous signal. And asynchronous is key here. It means the sender doesn't have to wait. It just sends the message and gets right back to work. So let's walk through how this actually works. It all starts when one process uses that exclamation mark to send a message to another. Now that message gets copied, it's never shared, and it's placed in the receiver's private little mailbox. This is where the magic really happens. The receiving process can check its mail. It can just grab the next message, sure. But what's really powerful is that it can use pattern matching to look through its whole mailbox and say, hey, I'm looking for this specific kind of message right now. It can pull out just the one it's ready to handle and leave everything else for later. This simple mailbox idea, it's the foundation for literally everything else. Okay, so this is all great, right? We have these tiny, isolated processes all communicating cleanly through messages. It's a fantastic model for concurrency. But what happens when something goes wrong? Because, things always go wrong. What happens when one of these little processes just crashes? And this brings us to what is probably Erlang's most famous, and let's be honest, most counterintuitive philosophy. Let it crash. Yep, you heard me right. Instead of stuffing every single process with tons of defensive code to handle every possible error you can imagine, the Erlang way is to just let a process fail. Let it crash quickly and loudly the moment it hits a problem it can't solve. Why? Because the job of fixing things, that belongs to someone else. And that someone else is a supervisor. See, in a real OTP application, you don't just have a random collection of processes. You organize them into what's called a supervision tree. You've got your worker processes, which do all the actual work, and then you have supervisor processes, whose one and only job is to watch over the workers. If a worker crashes, its supervisor instantly knows about it and can restart it from a clean, fresh state. You can even have supervisors that watch other supervisors, building up this incredibly powerful self-healing hierarchy. So how does a supervisor even know that a worker has died? Well, it uses one of two key tools: links or monitors. Think of a link as a suicide pact. It's a two-way connection. If one process dies, it sends an exit signal that automatically kills the other one too. You use this when two processes are so tightly coupled that one literally can't function without the other. But a monitor? That's different. That's what supervisors use. It's a one-way street. The supervisor watches the worker, but not the other way around. If the worker dies, the supervisor just gets a simple message in its mailbox, a down message, and it can decide what to do. It isn't forced to crash along with it. Okay, so we've got all these amazing concepts, right? Lightweight processes, clean message passing, and these self-healing supervisors. But imagine having to write the same code over and over again for every single process. Okay, set up my initial state, now start a loop, now wait for a message. That would get old really fast. And that's where OTP comes to the rescue again, by taking these common patterns and wrapping them up into something called a behavior. Here's the big idea, and it's brilliant. An OTP behavior splits the code into two parts: the generic, boilerplate stuff, and your specific business logic. Think of it like a pre-built engine. The Gen Server module, for example, gives you this battle-tested, rock-solid server loop for free. All you have to do is write a few specific functions, we call them callbacks, that fill in the blanks. You just tell it how to handle the messages that are unique to your application. And this is exactly how you'd build something like a super reliable router core. And this table just lays it out perfectly. This is the decision loop. The Gen Server gives clients a really clean way to talk to it. So if a client needs an answer and has to wait for it, it uses Gen Server call. That's a synchronous request, and it automatically triggers the handle call function in your code. But what if the client just wants to send a notification and move on? Then it uses Gen Server cast. That's a totally asynchronous, fire and forget kind of message, and it triggers your handle cast function. And for any other kind of message, like maybe that down notification we talked about from a monitor, that goes to handle info. See? The generic part handles routing the message. You just have to write the code that deals with it. Let's just trace a single synchronous call step by step to see how clean this is. Okay, step 1, a client process calls our router core, and then it just waits. It's blocked until it gets an answer. Step 2, the Gen Server process that is our router gets the request in its mailbox. Step 3, the generic Gen Server loop looks at the message and calls our specific handle call function. Step 4, our code does its thing. Maybe it looks up a route, and it returns a reply. Step 5, the generic server code takes that reply and sends it back to the client. And finally, step 6, the client unblocks, gets the answer, and happily continues on its way. It's a perfect, safe request-response cycle, all managed for you. All right, so let's zoom out for a second. When you take all of these pieces and put them together, the super lightweight processes, the totally isolated message passing, these amazing supervision trees, and the structured patterns like Gen Server, what you end up with is something, well, it's just incredibly powerful. So let's just recap the big wins here. First, you get massive concurrency because processes are so cheap. Second, you get true isolation from that share-nothing philosophy, which just wipes out a whole class of bugs. Third, you get unbelievable fault tolerance, thanks to those self-healing supervision trees and the whole let it crash idea. And finally, you get structured, reusable code by building on top of battle-tested OTP behaviors. It really is the whole package. And that really leaves us with one final big idea to think about. This isn't just a different syntax or a different way to write code. It's a completely different way to think about building systems. When the platform itself guarantees that one tiny little failure isn't going to bring down the whole ship, you can stop worrying about every little thing that could go wrong. You can stop writing paranoid, defensive code and start focusing on the big picture, on building truly resilient, large-scale architecture. So the real question is, what kind of problems could you solve if you had that kind of confidence?